So in this video, we're going to look at an important aspect that I've ignored so far for clarity or didactic reasons, which is how is the memory actually allocated in this device, and how do you know if you're about to run out of memory? So what you see here is the Texas Instruments data sheet for the device that's implemented on the EM60, the MSP430 FR5994. And you can see that the main memory, which is FRAM, it's a non-volatile form of RAM, which is used for both data and code, is 256 kbyte. By the way, many other controllers have just flash memory, which is good for code, but not data storage. FRAM is actually sort of a combination between RAM and flash. It's a little bit slower than RAM, though, so there are some performance aspects to that. But in any case, you can see here the memory mapping. They list it always from highest to lowest address. I would generally look at it the other way around, but so from hex 4000 to hex 43FFF is the main code memory. Part of that is actually the interrupt vectors, a small section in here, hardware interrupt vectors. And then we have this 4 kbyte of RAM that's shared with between the CPU and the LEA, the low energy accelerator or DSP coprocessor. Then we have RAM, so this is volatile, but it's the fastest form of memory here, and various other things. The memory allocation is defined in this file here, the .cmd file. And again, we already set this up to be suitable for applications, so you generally do not have to modify this at all. In some specialized cases, you might. And how it starts out here are memory segment definitions. Let's look, for example, for the code memory, which we call FRAM and FRAM2, a main code and data memory. Here the FRAM section has an origin at hex 8000 and goes for a length of 6FE0, and that gets you to the beginning of the application valid indicator, then application start, and so on. Notice there's a bulk data small section here. This is for large global variables. Even though it's called small, that's because there's another section. So starting at hex 4000 and another length of 4000. So if you needed more code space in the 64 kbyte area, so the 16-bit code space, you could make this smaller and this bigger if you wanted to. And then down here we have FRAM2, another big application code area. And then this bulk data big we reserved for more bulk data. So we don't really use dynamic memory allocation here. I don't like to use that in real-time systems, because in dynamic memory allocation, you might overlook some worst case scenario where you run out of memory. And so instead, if you have big data areas, you might just want to initialize a pointer to them, so you know exactly what you have, and make sure that you can make sure that you're not going to run out of code, out of memory here. Finally, here we have a definition of the LEA RAM, so that shared RAM between the CPU and the LEA. So this is this file here. Further down here now are data sections that are defined that use these defined code memory areas, like .text, which is application code, is stored there, is in FRAM or FRAM2. It can be stored, other stuff is stored in RAM. .bulk data small is stored here in the bulk data small section, and so on and so forth. moving on to a different file, which is important for you when you are using the acoustic signal processing using the LEA. So you have to make sure that you don't run out of LEA memory. And there's certain definitions. Here's SBUF DMA samples here, in this case 256, size of each of the two ping pong DMA buffers. That's specified here not in bytes, but in samples. One sample is 2 bytes. So we have 256 in each buffer, 512 total, and then a coefficient memory, which is used for FIR coefficients and FFT windowing, another 256 samples, so another 512 bytes, and then a results buffer, which is used for the FIR and must be the same as one of the two DMA buffers, so another 256. So what's the total here? 256 samples times 2 here makes 512 plus another 256 plus another 256 makes 1024. Could you use, so 1024 samples, could you double that if you wanted to do a 512 point FFT, for example? Then you would have to double this. So 512 times 2 is 1024. This one needs to be the same size, so that's 1K, 1.5 K samples. And that would still fit into the 1892 that's available out of the samples out of the total 4K byte or 2K samples when you account for the LEA stack that was defined in the last one. But if you also want to do FIR, then you need a results buffer, because unlike in the FFT, which stores the results in place, literally in the DMA ping pong buffer, it's stored externally for FIR filters in a different memory region. And so if you added this to it, made another 512 here typically, then you would actually be right at 4K by total 2048 samples, and that would exceed the 1892. So that wouldn't work anymore. Let's now look at appmemory.c, where this is being used. Here in this macro is the ping pong buffer definition. You can look up how that works out. And here's the coefficient buffer. And here is the results buffer. Here you see another example explicit, like the symbol table is used for, that's the symbol table for transmitting acoustic waveforms, and it's stored in bulk data small. Just going back here briefly to this, so where's this stored? Bulk data small. Here, and we have hex 4000 bytes, and we're using 1000, was it 1000? Yeah, symbol SMT. Actually, I don't know exactly how big the structure is, but you'd have to make sure it fits into bulk data small. Otherwise, you'd have to move it into bulk data big. So this is, you know, a use of the memory here, and down here in the .cmd file is the definition of all the memory regions. Now, once you've compiled your application, the question is, how much code space have you used up? And you can see that in the .map file that I just opened here. And here's all the various memory regions, origin, length, used and unused. Let's look at the code space, which is in FRAM and FRAM2. FRAM starts at hex 8000. The length is 6FE0. It's all hexadecimal stuff, of course. and used is only 13B0, so that's less than a quarter of the space used in FRAM, and that's for the EM60 test application, which does have quite a bit of code in it. And then here, looking at FRAM 2, we are using 9B92 out of hex 2000, so that's a little bit more than a quarter, somewhere between a quarter and a third of the memory is used in FRAM 2. Bulk data big, uses actually most stuff here, it looks like. Yeah, no, it doesn't. 55F0, and then 3 is EA10. So again, like a third or something like that. So that's how you can see how close you are to running out of memory. But really, this MCU can hold quite a bit of code. So you can have rather big code base there.